so I need to give you guys a funky function, which is the Dirac-Delta. So it should be noted that this is not a function in the traditional sense. Okay? Meaning I'm going to write a lot of shit up here that's not going to seem like it makes any sense at all. And yeah, just yell. It's fine. Like, don't sweat it. So I'm going to define this function. So this is going to be delta taking the argument of t minus t naught, which is going to be piecewise in the most horrible possible way. So it's going to be 0 if t isn't t naught. And I'm defining this, and this is the part where the yelling usually starts. Okay? I'm going to define this as 1 over 0 at t equals t naught. What do you mean, okay?
I've seen the Dirac before.
Okay, so there are other ways to define the Dirac-Delta function. Another way you could define the Dirac-Delta function is you could make some kind of approximations, right? And the way you'd make an approximation is you draw a picture. So I'd have, oops, I need an argument on that. So that'd be at t minus t naught. And so you'd put your t naught someplace, and then you'd go out, let's see, you go out 1, or to t naught plus 1 over n, and back to t naught minus 1 over n. You'd be 0 everywhere else. And then in there, you'd make a little triangle that looks like this that goes to n high. What's the area of this thing?
1.
Yeah, I think it's n tall by 2 over n wide. And it's a triangle, not a rectangle, right? Okay, so this has an area of 1. And then you could define this guy, so alternatively defined, you could take this as the limit as n tends to infinity of the delta n of t minus t naught. See that? Your book does this treatment more or less. I think they actually use a rectangle, but whatever. Okay.
So it's just.
I'm gonna do this dumb treatment just because there's a fun Calc 2 thing in there. If you want the other treatment, it's totally available in the book. He does a really nice job with it. I just like this other one because it's kind of a joke.
So
Right?
it's kind of always off except for one point where it's like sort of infinite, sort of.
Yeah, and if you look at other books, you'll see that sometimes they'll define delta t minus t naught as 0 or infinity. And I like the aesthetics of the 1 over 0, and let me show you why. So I want to integrate from, let me just for kicks, integrate from t naught to t naught, delta of t minus t naught dt, right? And according to everything I was saying when we were doing the unit step function stuff, this should be 0, right? Because, well, it's the area under a point, right? It should be the, I mean, if you go to Riemann sum land, right? It should be the, should be the width of the rectangle, right?
That's it.
No, it's not the area of a rectangle.
It's gonna be that.
Should be the width of the rectangle times the height of the rectangle. The height of this rectangle is, right, over t naught is 1 over 0.
Oh, that's cancel.
And they cancel, so you get 1.
See, I guess that's where you incite.
Right? They just like cross out. It's fine. Alternatively, you could treat the little triangles and then pretty clearly, right? If you take the limit of the integrals of those guys, right, they'll all always be 1. So if you interchange that order, which I told you was a little funky, right? But if you assumed you could interchange that order, you'd get the same thing out of it.
So this is, it actually always has an area of 1, right?
Yeah. Yep. So this thing has an area of 1 underneath that one funny rectangle that's 0 wide and infinitely tall.
It's just a limit.
Yeah, it's basically a massaging of limits thing. This is, you could develop this with a thing called the theory of distributions, but the theory of distributions is like it's like a big textbook about like yay big, and it's usually dusty in the back of the library because. But it's a weird, it's kind of an orphan. The theory of distributions was kind of largely done a long time ago, and so mathematicians kind of know that it exists and that everything in it was verified 100 years ago. And yeah, it gets looked at sometimes by applied guys, but I don't know any of them.
I was wondering, you said you could kind of interchangeably use infinity and 1 over 0. If you got to the end, it'd be 0 times infinity. Is it just an identity that that's 1? Because in that case...
No, that's why I like to define it this way. So that it's kind of like, oh, well, they just cancel and you get 1 out. The right way to do this is with this kind of area picture. Right? This thing is also kind of reasonable, but you have to kind of convince yourself that 0 times infinity should be 1, and it's not really reasonable, but it should be, right? You guys all okay with kind of? Okay. So let me Laplace transform this thing then. Okay.
What was that?
It got stuck to the board and flipped over in my hand. Okay, so if I would like to Laplace transform delta of t minus t naught. I should do, yeah, do the definition. So definition-wise, this should be the integral from 0 to infinity of e to the minus st times the delta function dt. Right? But this thing's like basically always 0 except at the one spot, right? So you break this up, and it's the integral from 0 to t naught of e to the minus st times 0 dt, plus the integral from t naught to t naught. I know this feels weird. This is kind of me thinking t is strictly smaller than t naught. And this is me thinking t equals t naught and t equals t naught. And I have an e to the minus st times, yeah, I'm going to put a delta of t minus t naught in there for a second. And then plus the integral from t naught to infinity of, and really that's t is just a little bit bigger than t naught, right? And this is why that limit thing kind of comes into play here. And then an e to the minus st and a delta, oh, not a delta, just a big fat 0, dt. And then you go, well, that piece is clearly 0, and that piece is clearly 0, and this piece is screwy. So I need to wonder, just from my similar thought over there, right? The width of this rectangle and the height. So I'm left with this thing, right? I'm left with t naught to t naught, e to the minus st, and then a delta of t minus t naught dt. And then if I think about this as a rectangle, how wide is the rectangle? 0 wide. What's delta t naught? 1 over 0. And what's this guy at t naught? It's e to the minus s times t naught. So all told out of this, you get that the Laplace transform of delta of t minus t naught is e to the minus s t naught.
So this gives us a scalar, always?
So this gives us a scalar function of s, right?
Oh,
So this gives you e to the minus scalar s. See that? So what's the difference between the delta and the unit step function? This delta didn't have anything attached to it, right? You guys see that?
Yeah.
Like my e to the minus s
Yeah,
t
there was
naught
no f of t stuck on
had
it.
no like other function of s stuck to it.
Oh.
You guys see that? So what if there was a function times a Dirac-Delta? Yeah, then we'd have just a function evaluated at a point, right? So we'd have a constant here. It would actually be a constant there, right? You guys cool with that?
Why would that turn into a constant? Oh,
Because it's the height of the rectangle,
Yeah.
right? The height of this, so this piece here is just modifying the height of your rectangle. And you're always going to evaluate it at t equals t naught. So maybe let me write that down.
So you're actually allowing us to divide by 0.
I'm not allowing you to divide by 0, I'm telling you to divide by 0.
This seems like something that there's like a really formal, like nice, correct
Yep,
proof way, way higher up than this, right?
yep, that's exactly true. The only time I've ever seen the theory of distributions developed was developed solely so that I could see this, right? Because this is the thing that that pure mathematicians use the theory of distributions to do. Applied people use it for a couple other things, but this is the one that I've seen personally. Cool. What's the point of the Dirac-Delta function? Impulse. Yeah, this is when you have your, like, totally, which one is it when there's, like, what's the model for hitting a billiard ball with a hammer? Is that elastic or inelastic? I always forget which way they go.
That's elastic.
Alas.
Elastic is when it's
Yeah,
all
when
that
they
force
stick
is
together.
transferred instantaneously.
Inelastic just means they
Stick together.
Yeah.
See, that doesn't make any sense. Elastic things tend to. Never mind. Yeah, so you use this for the spring system that you start by whacking it with a hammer. So that'd be like, you'd have some spring system, right? So AY double prime plus BY prime plus CY is, and then Y prime at 0 is 0, and Y at 0 is 0. Right, so this is your spring just chilling. And then you're going to give that thing a solid whack at time 3.
So in physics though, like the time is never really 0. Is this thing not really a 0, 2, and that's why we can...
This thing actually does a nice job of modeling things that seem to take no time. So if there's no observable time, right, if there's no observable deformation of your two objects, this is probably a better model than cobbling together some,
Yeah.
like, oh, it never takes exactly 0 time, it just takes a, 1/10 of a nanosecond or whatever. This is probably the model you want anyway. And it should be noted that this is just a model anyhow, right? That's kind of good with this idea?